Engines are fascinating machines that convert energy from one form to another to produce mechanical work, typically motion. While there are various types, the most common categories are internal combustion engines, ICEs, and electric motors. Let's delve into an in-depth explanation of how they work. Internal combustion engines, ICEs. Internal combustion engines, as the name suggests, burn fuel inside the engine itself to create power. This combustion generates high-temperature, high-pressure gases that exert force to move components, ultimately leading to rotational motion. Key components of an ICE. Before we discuss the cycles, let's understand the main components. Cylinder. A cylindrical chamber where combustion takes place. Engines can have multiple cylinders, e.g., 4-cylinder, V6, V8, etc. Piston. A cylindrical component that moves up and down within the cylinder, driven by the expanding gases. Connecting rod. Connects the piston to the crankshaft, converting the piston's linear motion into rotational motion. Crankshaft. A rotating shaft that receives the force from the pistons, via the connecting rods, and converts it into usable rotational energy. This is what ultimately drives the wheels of a vehicle or powers other machinery. Cylinder head. Sits atop the engine block, sealing the cylinders. It houses the valves and spark plugs in gasoline engines, or fuel injectors in diesel engines. Valves, intake and exhaust. Precisely timed openings that control the flow of the air-fuel mixture into the cylinder and exhaust gases out of the cylinder. Camshaft. A rotating shaft with eccentric lobes, cams, that push open and close the intake and exhaust valves at the correct times. It's connected to the crankshaft by a timing belt or chain. Spark plug. Gasoline engines. An electrical device that generates a spark to ignite the air-fuel mixture. Fuel injector. Diesel engines and modern gasoline engines. Sprays fuel into the cylinder or intake manifold. Combustion chamber. The space within the cylinder where the air-fuel mixture is ignited and burned. Engine block. The main structure of the engine, containing the cylinders and often passages for coolant and oil. Oil pan. Sump. Collects and stores engine oil for lubrication. Flywheel. A heavy disc attached to the crankshaft that helps smooth out the engine's rotation and store kinetic energy. Types of internal combustion engines. The two most common types of ICEs in production are 1. Spark ignition, gasoline engines. Fuel, gasoline, is mixed with air before being inducted into the cylinder. The mixture is compressed and then ignited by a spark from the spark plug. Most operate on the Otto cycle. 2. Compression ignition, diesel engines. Only air is inducted into the cylinder and highly compressed, causing its temperature to rise significantly. Fuel, diesel, is then injected into this hot compressed air, causing it to spontaneously ignite, compression ignition. Most operate on the diesel cycle. The 4-stroke cycle, common to both gasoline and diesel engines. Most modern ICEs operate on a 4-stroke cycle, meaning 4 distinct piston strokes, up or down movements, are required to complete one power cycle. These strokes are 1. Intake stroke. Process. The piston moves downwards, creating a vacuum in the cylinder. The intake valve opens, and a mixture of air and fuel, gasoline engine, or just air, diesel engine, is drawn into the cylinder. Analogy. Imagine sucking air into a syringe. 2. Compression stroke. Process. Both intake and exhaust valves close, sealing the cylinder. The piston moves upwards, compressing the air-fuel mixture, gasoline, or just air, diesel, in the cylinder. This compression significantly increases the pressure and temperature of the gas. Analogy. Pushing the plunger of a sealed syringe, feeling the resistance as the air compresses. 3. Combustion/power stroke. Working stroke. Process. Gasoline. At or near the top of the compression stroke, the spark plug fires, igniting the compressed air-fuel mixture. This causes a rapid, controlled explosion, generating a massive increase in pressure and temperature. The expanding hot gases forcefully push the piston downwards. This is the stroke that produces usable power. Process. Diesel. At or near the top of the compression stroke, fuel is injected into the highly compressed hot air. The high temperature of the air ignites the fuel, leading to combustion and rapid expansion of gases, pushing the piston downwards. Analogy. The force felt when the air in the syringe is heated and expands rapidly. 4. Exhaust stroke. Process. The piston moves upwards again, and the exhaust valve opens. The rising piston pushes the burned gases out of the cylinder and into the exhaust manifold, which then leads to the exhaust system and out into the atmosphere. Analogy. Pushing the plunger of the syringe to expel the contents. Once the exhaust stroke is complete, the cycle repeats, starting again with the intake stroke. The continuous repetition of these 4 strokes generates continuous rotational motion of the crankshaft, which is then transmitted to the wheels in a vehicle or other driven components. Thermodynamic cycles, Otto versus diesel. While the mechanical strokes are similar, the thermodynamic processes differ. Otto cycle, idealized for gasoline engines. Intake, Isobaric expansion, constant pressure, as air-fuel mixture enters. Compression, isentropic, adiabatic and reversible, no heat transfer. Compression of the mixture, pressure and temperature increase. Heat addition, isochoric, constant volume, heat addition, combustion. This is where the spark plug ignites the mixture, causing a rapid pressure and temperature rise at constant volume. Expansion, power stroke, isentropic expansion of the hot gases, pushing the piston down and doing work. Heat rejection, isochoric heat rejection. Exhaust valve opens and hot gases escape, constant volume cooling. Exhaust, isobaric compression, constant pressure, as exhaust gases are expelled. Diesel cycle, idealized for diesel engines. Intake, similar to Otto cycle, air only. Compression, isentropic compression of air only, leading to much higher compression ratios and temperatures than in an Otto cycle. Heat addition, isobaric, constant pressure, heat addition. Fuel is injected and burns, with combustion occurring as the piston moves slightly, maintaining a relatively constant pressure. Expansion, power stroke, isentropic expansion of the hot gases, doing work. Heat rejection and exhaust, similar to Otto cycle. The key difference lies in the heat addition phase, constant volume for Otto, spark ignition, and constant pressure for diesel, compression ignition. Other internal combustion engine types. While four-stroke piston engines are dominant, other ICEs exist. Two-stroke engines. These engines complete a power cycle in just 2 piston strokes, 1 revolution of the crankshaft. They combine intake/compression and combustion/exhaust, often using ports in the cylinder walls instead of valves. They are simpler and lighter, but generally less fuel efficient, and produce more emissions. Commonly found in smaller applications, like lawnmowers, chainsaws, and some motorcycles. Gas turbine engines, jet engines. These engines work on a continuous combustion principle, Brayton cycle. Air is continuously drawn in by a compressor, compressed, mixed with fuel and ignited in a combustion chamber, and then the hot, high-pressure gases expand through a turbine. This turbine drives the compressor, and the remaining high-velocity exhaust gases create thrust in jet engines, or drive a generator in power plants. They are powerful and efficient for their weight, used in aircraft, power generation, and marine propulsion. Electric motors. Electric motors convert electrical energy directly into mechanical energy, motion, through the interaction of magnetic fields and electric currents. Fundamental principle, electromagnetism. The operation of electric motors is based on 2 fundamental principles of electromagnetism. 1. Magnetic fields. Electric currents create magnetic fields. Conversely, changing magnetic fields can induce electric currents. 2. Lorentz force. A current-carrying conductor placed in a magnetic field experiences a force. This force is perpendicular to both the direction of the current and the magnetic field. This force is what ultimately creates torque and rotation. Key components of an electric motor. Stator, the stationary part of the motor. It contains coils of wire, windings, or permanent magnets that create a stationary magnetic field. Rotor, the rotating part of the motor, located inside the stator. It also contains coils of wire or permanent magnets. Windings, coils of wire, usually made of copper, that carry electric current. When current flows through them, they become electromagnets. Commutator, DC motors, a segmented cylindrical device that reverses the direction of current in the rotor coils at specific points during rotation, ensuring continuous rotation in one direction. Brushes, DC motors, stationary contacts that press against the commutator to transfer electrical current to the rotating rotor windings. Magnets, permanent or electromagnets, create the magnetic fields necessary for the motor's operation. How an electric motor works. Simplified DC motor example. 1. Magnetic field creation. The stator, either through permanent magnets or energized coils, electromagnets, creates a stationary magnetic field. 2. Current in rotor. Electric current is supplied to the coils in the rotor. This current transforms the rotor coils into temporary electromagnets. 3. Interaction and force. The magnetic field of the rotor, created by the current, interacts with the magnetic field of the stator. This interaction creates a force, Lorentz force, that attempts to align the magnetic poles. 4. Rotation. Due to the design of the motor, this force causes the rotor to rotate. In a DC motor, the commutator and brushes continuously reverse the direction of the current in the rotor coils as it rotates. This ensures that the magnetic poles of the rotor are always repelled by the like poles of the stator and attracted to the opposite poles, creating continuous rotational torque in one direction. 5. AC motors. In AC motors, the alternating current in the stator windings creates a rotating magnetic field that drags the rotor along, eliminating the need for brushes and commutators in many designs, like induction motors. Types of electric motors. DC motors. Direct current. Powered by direct current. They are known for their good starting torque and speed control. Brushed DC motors. Use brushes and a commutator. Brushless DC, BLDC motors use electronic controllers to switch current to the windings, eliminating brushes and offering higher efficiency and longevity. AC motors, alternating current, powered by alternating current. Induction motors, the most common type of AC motor, known for their robustness and widespread industrial use. The rotor current is induced by the rotating magnetic field of the stator. Synchronous motors. The rotor rotates at the same speed as the stator's magnetic field, used in applications requiring precise speed control. Conclusion. Both internal combustion engines and electric motors are ingenious devices that convert energy into motion. ICEs achieve this through controlled explosions of fuel, following a cyclical process of intake, compression, combustion, and exhaust. Electric motors, on the other hand, harness the fundamental principles of electromagnetism, using the interaction of magnetic fields and electric currents to create continuous rotation. The choice between these engine types depends on the specific application, considering factors like power requirements, fuel type, efficiency, and environmental impact.